Good afternoon. Who's there? Looks like there's one person, unless that's me viewing myself. I really apologize for what happened in the morning, but I think I fixed everything now. And yeah, people are coming on. Good. And I lost the chat, so that's not so great. Hopefully there'll be no interruptions, so we won't. If there's interruptions, we lose the chat. I don't know how to recover it. It's seen as like an edit. So yeah, we lose the chat. So hopefully that won't happen. So where we left off, I had discussed distributions and how to summarize distributions for presentations and reports, or just to understand your variable better. And I explained first, you have to display the distribution in a graphical visual format and determine whether the distribution is symmetric or skewed, because that will determine what statistics you use. Because we are going to focus on symmetric distributions, I'm going to demonstrate. Well, first we talked about the center, or the expected value of the distribution when the shape is symmetric, and we discussed how we should use the mean. Even though the mean, the mode, and the median will have the same value approximately when the distribution is symmetric, we prefer, and by convention, use the mean, and a lot of statistic theory has been developed using the mean. In terms of the variation in the values that you expect, we calculate a measure of spread of the distribution. So one thing to think about when you think about the range of values, you could think about the minimum value, the maximum value. But how, I want to put together the distribution with focus on the center, because the center is the expected value. And so the way we're going to look at this is from the center, how do the values of the distribution vary with respect to the center? Okay, so statistics is about averages or measures of expected value and relative measures relative to the expected value. So you'll see that the spread is going to be just that. It's going to be a measure of how spread out the values are. A range of values is one thing. A range could be from minimum to maximum, but a measure of spread is more about picking up, anyway, we'll see. Let's talk about how a measure of spread differs from a minimum and a maximum, right? So when it comes to when the data are skewed, like the example that we looked at with the grocery store, we would use the median as the center, and to describe the spread, we would report the minimum, the maximum, and the 4 quartiles. So minimum, maximum, and then what's in between. What's in between, you can divide up the data into the first half. That would be marked by the median. But then you could also split up half of the data into lower half and upper half, and then between those identify 25% or a quarter of the data. So dividing the data in quarters, so the first 25% of the observations, and find out what is the maximum of the first 25%. And then you can find the maximum of the second 25%, which is actually the median. And then you find the maximum of the next 25%, which is the 75th percentile, and then the maximum value overall. So dividing data like that is not something we're going to be doing in this class, but that's what you would do if the data are skewed. If the data are symmetric, we compute the mean and report it. And then for spread, we report the standard deviation. So I'm going to review the calculation of the standard deviation, the meaning, and its interpretation. This is critical that you understand this, okay? Again, statistics is about averages and relative measures. So you need to know an average and you need to know computing the most basic relative measure, the standard deviation. So here's an example. So I take these, very simple examples, and I usually talk about money because our brain learned numbers for the purpose of trade, or so evolutionary scientists would say. So we're really adept to understanding numbers when we talk about money. So here's another example with regarding money. What you have here is a list of the days of the week, Monday, Tuesday, Wednesday, Thursday, Friday, in a select week, where the amount of money a student had in their pocket they happen to have for spending, coins or bills. This is how much they had available in their pocket throughout the week. We want to answer the question, how much money can she expect to have in her pocket in a given week? Now, this might not seem so interesting, but this could be useful, let's say, in in a cafeteria type setting. They want to know how much pocket money people have or tend to have. And so they just look at one student, and this is not a great sample, but it's just an example for you, okay? It's not a great data sample because there's only 5 observations, but I want to use it to illustrate the calculation of the standard deviation. So we begin by looking at the data. Here are the numbers. And considering, the first issue is, are these data symmetric? Well, it's not a lot of it, and graphing that is weird. There's too few data points to actually graph it. So we've got to think about it. Because if we use the average, we have to make an assumption. We're assuming when we use the average that the data is spread out symmetrically. So let's take a moment to look at that. If we take 2, so let's put them in order. 2, 5, 8, 10, and 16. Okay, so 8 is in the middle. My pen is needs to be adjusted. Okay. So 8 is in the middle. And then, are these evenly distributed? Like, this is about 3 over here, right, to get to 5. And then this is about 2. So that's kind of evenly spread out. And then to go further a bit, 5 to 2 is another 3, and then 10 to 6 is 6. Okay, so that's not perfect. It's not perfectly evenly weighted on both sides. But I'm going to make, again, an executive decision. Remember, I mentioned to you we have to do that. So I'm just going to make an assumption that this data comes from a symmetric distribution. So it's a really rough way to look at things, but I hope you follow my logic. All right, so I need to erase that because I need that space. All right, so what we're going to do next is we're going to calculate the mean. I'll talk about that formula in a moment, but we'll start with this formula. This is the formula for the sample mean. The sample mean is a sum, this represents sum, of all the values that are then divided by how many values there are. So whenever you see something like this, whenever you see this sign, this is also a sigma, but it's a capital letter sigma in Greek, and it says sum, add up, all of these values. And sometimes you see this with a subscript, you know, I equals 1 to n, but it's left out because it's kind of obvious. Like it becomes obvious that's what we're doing. Because the n is telling you here that there's going to be n that we're going to average. So whenever you see this symbol from now on with a sigma and an n on the bottom here, this is always going to be, we're going to refer to this as an average. Actually, I'm not going to put quotes around it. I'm just going to refer to it as an average. And when we see something similar to it, we're going to call that an average too, all right? And we're going to put quotes around it. And I shouldn't put quotes around this because I don't want to be confusing. I'll just say sigma means sum. See, now I'm saying means and it sounds confusing. Wait, let me fix that. Okay, sigma for sum, that's what I'm going to say. Sigma for sum. Greek letter. Oops. Greek letter S for sum. So the average, we're going to do this with our calculators. We're going to use the financial calculator, and we're going to enter in these values and ask for the average. So 2, 8, 10, 16, 5. I'm going to pull up the financial calculator. And I'm going to clear the screen. And what I'm going to activate now is the statistical mode in the calculator. And to do that, I hit second data. Now you see something's in there already, so I need to clear that. So second clear work clears a worksheet for statistical data. So I hope you have your calculator and you can try that. You should have your calculator to try that. This is pretty much where we're heading with this, is using our calculator to make statistical calculations, computations. So I'm going to enter each value to enter, and then I scroll down and it asks me for y. Entering x and y, it only happens when I have two variables. But right now I'm focusing on one variable. I'm not interested in two variable relationships. I'm just looking at one variable, in particular pocket money. So I'm going to skip over that. I'm going to leave it as a 1 and scroll down again. And then enter the next value. So what's the next value? 2, 8, 10, 16, 5, right? So 2, 8, enter down, down. 10, enter down, down. 16, enter down, down, and 5, enter down, down. Do you have all that? So you're just entering into X. And now we can scroll through and see that we have everything. So the first one, the value, so we use X as a symbol of the data, okay? So X, the first observation is 2, and we're not going to use Y, it just has a 1 in there. The second observation is 8, the third observation is 10, the fourth is 16, and the fifth is 5. And now I'm going to ask for the results. To get the results, I hit second stat. And it shows LIN. What does LIN stand for, do you think? What does LIN represent? LIN stands for linear. So this calculator has the capability of correlating two variables, X and Y, and determining whether the parameters of their linear relationship. So statistics associated with the linear relationship. So basically, the y-intercept, the slope, and the correlation between the observations on in a scatter plot for that, where that line is the best fit line to the scatter plot. So I'm going to talk about this again later, because right now I'm just looking at one variable. So if you didn't understand what I just said, it's fine. So I want the results. I'm going to scroll through the results with the down arrow. It tells me there were 5 observations entered. The mean is 8.2. This is 5.3 SX. And then this is 4.7. And then it starts to tell me about Y, which I'm not interested in right now. So I'm going to stop there. So I need to ask, what are all these values? So this is the mean, $8.20. And what's this? And what's this? What's the difference between those two? So this is the mean. Let's go to the mean. It's $8.20. And then you were given SX is equal to 5, and I'm going to round this because these are dollars, right? So 531. And then you were given this symbol and told the number was 475 if I round it to decimals, to 2 decimals. So which one should you use? Which one is your standard deviation? This is the sample standard deviation, which I want to try and calculate next. This is the sample standard deviation calculated like this. But this, what is this one? So SX is the sample standard deviation. It's $5.31. This one is the, I'm going to write it out in words. Oh, I think I hit the keyboard. Very weird. So this one is called the sample standard deviation, and this one is called the population standard deviation. Let's look at the formula. Actually, I want to make that in, I'll make it in a different color. What's up with this formula? What is this formula doing? What do you see in this formula that looks familiar? I see the sigma that I had over here. So this is summing something. It's summing this squared. And then it's doing this. So this is an example of what I was talking about out here, where when you see the sigma sign and an n nearby, this pattern indicates that you're computing an average. So this is what I'm going to call an average with quotes around it, because it's not that I'm dividing by n, I'm going to divide by one less. And the reason for dividing by one less has to do with the fact that in this formula, I'm using another statistic to get a statistic. When you do that, you lose what's known as a degree of freedom, okay? Because every value you introduce into a computation introduces a degree of randomness. When you tie those values together in some way in a calculation like this and then introduce that into your formula, you lose one degree of randomness. And so when you divide, when you average to get a representation of what to expect, we adjust our denominator, making it smaller by however many degrees of randomness. So for this variable, for the standard deviation, there's only one statistic over here, so we take away 1 degree of randomness. In other formula, there might be 2 or 3 or more statistics in the formula, and so you'd have to take more, 2, 3, and 4 degrees of randomness off, okay? We don't have to worry about that right now, but that's the pattern. So what's going on here is this is an estimate of the population standard deviation. If I actually had all of the data from the population, I wouldn't use X bar here. I would use the actual population mean. And then because I'm using the actual population mean, I don't lose a degree of randomness. So what I'm saying is, so without talking about all the rest of what's going on here, this is the formula for the population standard deviation. Rather than X bar, I should put mu in there. And rather than -1, I get to use, well, the population size. So n represents the population size, and little n represents the sample size. And it turns out, now looking at this, notice that the standard deviation of the sample is larger than the standard deviation of the population. If we were to think that this data was a population, from a population. So what this does is it forces, by making this smaller, the overall number is bigger and it shows me a greater range. This is useful to be able to be sure that you're capturing the essence of the data, because I'm going to show you how I use this number in a moment, but this number ends up being bigger, and it's an adjustment that's made. It turns out you can actually prove this is a good way to adjust the data so that your estimate standard deviation, sample standard deviation, is pretty good. We say it's unbiased. All right, so otherwise, if you divide it by n, it would be smaller. This is dividing by n, treating that sample as though it was the population and dividing by just n, and you would have a smaller overall number. So this allows it to be bigger and to capture the range of data in this way. Okay, so what's going on with this formula? What is this part now? This is really what we're interested in. I'm going to refer to this as the deviation from the mean. What we really want to do is look at how the values differ from the expected value. So I'm going to create a variable called deviations from the mean, and then I'm going to square them. I have to explain why I square them, and then I'm going to average them. So I'm basically, this is an average of the deviations from the mean. All right. So that's useful because it's telling me how far are all the values off from the mean. That's what I want to capture. So let me clean up this a little bit. We know this is for the sample, and we know this is for the population, and we don't want this one because we don't have a population, we have a sample. And what we want to do is calculate deviations from the mean. So the way to do that is to take each value and minus off, in each case, the mean. So you can do that all the way across and put the values in. Now remember, keep in mind these are all dollars, so these are all dollars here, right? Dollars, dollars, dollars.
And these are dollars, dollars, dollars. Everything is dollars. I don't have to keep writing it. I hope you understand. Those are all dollars all the way down. Okay, so now what? So let's say I just did this and computed the deviations from the mean, and then I guess I can just shade it. So these are the deviations from the mean. Why don't I just average those? Why don't you just average the deviations from the mean? Why don't we just do that? Why do we go through all this other stuff? So take a moment and enter those values into your calculator and calculate the average of these values. So I'm going to go to the calculator. I'm going to enter these. I'm going to clear my work. So go to data and then clear work. So now I enter 6.2 negative, enter down, down, and 0.2 negative, enter down, down, and 1.8, enter down, down, 7.8, enter down, down, and 3.2 negative, enter down, down. So that's my data. 6.2, negative 0.2, 1.8, 7.8, and negative 3.2. And then I'm just going to do second stat, scroll through, and now I see, oh, the mean is 0. Is that correct? The mean is 0. So the average deviation from the mean, does that actually make sense? That the mean would be 0? In fact, the average of the deviations from the mean will always give you 0, not just for this data set, for any data set. The average deviations from the mean will always be 0 as a result of the conversation we had over here. The mean is the value that sits to balance the number of observations and their value over here against the number of observations and their value over here. So it sits perfectly between the points in a way that it's closest, we say closest to all the points or values. Okay, so it sits in a way that, so it sits in a way that it's closest to all of the other values. It's the value that balances. It's like a mediator, right? It's like a mediator of all the values over here. If you think about these as relationships, it's closest to all of the other observations on either side, and it's like a mediator between them. So it's closest to all the other values, sitting perfectly in a balancing point of all the other values, their quantity and their magnitude, like what they are. So because of that, that's great and everything, but the issue is, if I'm going to talk about deviations from the mean on the left and deviations from the mean on the right, we're going to have an issue because taking each value and subtracting the mean, this amount, all of these values will end up being, because they're smaller than the mean, they're going to be negative deviations. Is this all too small? I'm going to make this bigger. Hold on. And the values on this side, where each of the values are bigger than the mean, will be positive deviations. And because the values, I have to fix that, it's bothering me. So just to repeat, the calculations of the deviations on below the mean will be negative. The deviations above the mean will be positive. And it turns out that if I add them all up, I'll get 0. So it's always going to be 0. So how do I resolve that issue? I want a measure of how spread out from the mean the other values are. Did I go too fast? In case you want to take a screenshot. So the sum of all deviations will be 0. So the average of all deviations will also be 0. That's not helpful. That's not helpful. And it'll always be 0, 1. And we just did an example here, and I demonstrated if you total these, the total will be 0. Well, the average will be 0, but it's because the total will be 0. So to avoid, to actually try and get some information out of this, we want to retain the magnitude of the deviation from the mean. We don't care about the sign, right? We don't care about the sign. One thing you could do is just drop the sign and just care about the fact that this one is far from the mean, this one is close to the mean, this one is far, this one is really far from the mean, and this one is moderately far from the mean. That's what I care about. I don't care if it's below or above. So that's one thing you can do, but statisticians did not end up developing rigorous methods. Well, they did, but another way that became more popular was to actually square these values instead. If you square these values, you get rid of the sign, right? And then all we have to do after we do the average is take the square root to eliminate the effect of squaring. So that's where this formula comes from. So let's see what this does. If I square each of these, I hope you're doing this as you go along. If you haven't, just rewind the video and start over, because it's much more meaningful when you do it than when I do it. Now, will I ask you to do a table? I'm going to illustrate with tables. You should be able to make table calculations, but it's not my priority that you're going to do it all the time. But you should be able to do this with no problem. So if I square all of these values, and I keep 2 decimal places, well, it'll give me 2 decimal places. So if I do that, oh, I'm losing my columns, my rows. Let's do that again. So this would be 0.04. This one would be 3.24. And 780 would be 60.84. And this will be 10.24. Is that what you get? Yes, one. And I appreciate any of your questions so that the other students can follow our conversation. I'm pretty sure the chat will not disappear this time. Okay. So you got that? Now my question is, are these in dollars? Like these were in dollars, and the mean was in dollars, and then the deviations from the mean, which I'll write down here so we know, these are called the deviations . So is this in dollars? So keeping in mind that what we did was square, whatever you do to the values, you also do to the mean. I mean, whatever you do to the values, you also do to the units. So these were dollars, so these were values squared, so I squared them, but I also have to square the units. In fact, the units here are really dollars squared, but that doesn't make any sense, so we don't say that or write that, but we can't forget it. So much so that at the end of this calculation, after we average, we have to take the square off so that we can return to talking about dollar units. Okay, so what we're going to do next is we're going to sum these values. Let me know if you have a question about what I just said. So you see, you could clearly do that. You can easily do this in Excel. So what do you get when you sum? We're not there yet, Juan. I want to finish the calculation and then I'll tell you about it. So what's the total? The total is 112.80, I think. Is that what you get? So once you have the total, let's see what we have to do next. So we have this, we have all of this done. That's the total, sum total. Now we have to average. We're going to average, but not exactly dividing by 5. We're going to divide by 1 less because I told you need to do that because this is a statistic and that's a correction for degrees of freedom. So we calculate S equal to the square root of 11280 divided by 4. This is actually the square root of what's called the variance. So that inside part, before you square root it, before you return it to dollars, is called the variance. So the variance is actually the average of the square deviations from the mean. And the square root of that is the standard deviation. And the reason for the square root, again, is to get it back in dollars. So when you do these steps, you get that this is $5.31. So now I can put the dollar sign back. In all these steps, I cannot have a dollar sign. Oh, see, I did it there. It's wrong. There's no dollar sign there. Okay, so it should have no dollar signs in any of these calculations until the very end. So now, we got the result we were expecting up here from our calculator. Now what do we do with it? The larger the standard deviation, the more spread out the observations. Now it's all relative, right? Because what is large and what is small depends on the values we're working with. So I need to combine to interpret these results, I need to combine the measure of the expected value with the standard deviation to make it meaningful. And in conclusion, what we say is she spends about $8.20 on average a day, right? Give or take $5.31. So I'm going to show you how to interpret that. Since the data is roughly symmetric, the way we can interpret that is this. We make an interval between plus and minus x bar and s, okay? The mean, give or take. This is the give or take. So let's make an interval between $8.20, give or take $5.31. So that's an interval of 1 standard deviation. What would be the lower and the upper limits for that? This would be $2.89, and then the upper limit would be $13.51. Now, so this is saying that most of the observations, that's how you interpret 1 standard deviation. Well, let me write it in words below. Most of the observations, so the majority, will be found 1 standard deviation from the mean. So now let's go back to the data and see how many of the observations fall in here. So go back to the data and see. Does 2 fall in that interval? No, right? Because it starts at 289. Does 8? Yes. 10? Yes. Not 16 and 5. So we actually see that in 1 standard deviation, no, not that one. In 1 standard deviation, we capture 8. Oh my goodness. 8, 10, and 5. So 3 out of the 5, or 60%, are within 1 standard deviation of the mean. That's the meaning of most. Now, it's, you guys, oh my goodness. You guys don't need to know, I'm not going to go through all the proofs of all of this, but it turns out that, in fact, working with the mean and standard deviation like this, there's a theorem, I think it's Chebyshev's theorem, that proves that you will have the majority of the data within 1 standard deviation. So, but it's not all of it, and it's not, it's 60%. That's what we've got here. What about the rest of it? So the two numbers together give a reader, or give an analyst an idea of how spread out the values are. Okay, so most of the time it's going to be between $3 and about $14 that the person has in their pocket. What about the rest? Can we expect the observations within 2 standard deviations? Let's do that. So let's write it. Let me draw a line. Actually, I learned how to do the lines nicely. How did I do that? Oh, I used this. And I went like... I'll do that one more time. Oh, it's okay. So let's do 2 standard deviations from the mean. So in 2 standard deviations from the mean, what do we find? Oh, I just cut the data. That's interesting. I didn't know I had the power to do that. Okay, so 2 standard deviations from the mean means I take $8.20 plus or minus 2 times $5.31. So what is that interval? So that actually goes into the negatives, which is okay. So now, within 2 standard deviations, we find all of the data, right? Everything falls within there. So we are able to represent with 2 numbers an expression that captures how spread out the data are. So if you give or take 2 standard deviations, that's all the data. So it's pretty tight. Okay, it's a tight distribution because all the data falls within 2 standard deviations. A more spread out or more volatile distribution would be one that is more than 2. Actually, and this goes back to the question I left off the first part of the lecture with earlier today, when I asked you what would constitute an outlier for symmetric data. In symmetric data, oh, you can't see what I wrote there, right? Let me put this up higher. Okay, so I'll repeat because my my page was too low down. So you see all the values fall in this range, so it's 100%. And I said that this is a tight distribution. In symmetric data, if the distribution is more volatile, you can actually see what are called outliers. Outliers are actually found outside of or beyond do you know? Does anybody know? This is the bell. Specifically, 3 standard deviations. So we usually say roughly beyond 3 standard deviations are outliers. They are infrequent unlikely, but they exist. They're possible, but improbable. Let's see. In this distribution, they're not possible. There's different ways to assess outliers with symmetric data, and there's just different techniques for outliers in different scenarios. But when you use the mean and standard deviation to determine outliers of a single distribution, this is what you do. You look and say, is it beyond 3 standard deviations? If there's values there, it's part of the data, but we could start to refer to them as extreme values or outliers if they are beyond 3 standard deviations. Also, it's worthy of investigation to make sure someone didn't make a data entry error or they didn't record a measurement properly. Those are 2 different things. You can measure something incorrectly. So, for instance, this girl, she had $2. Let's say $2 turned out to be an outlier. Maybe she had some money in her back pocket that wasn't measured properly, so that's a measurement error. If someone was typing the numbers down into Excel and they wrote a number wrong, that's called a data entry error. So errors like that could be possible, and if you see outliers, you should make sure that those are correctly entered and correctly measured to keep them. Okay, so we've learned how to calculate the standard deviation, how to use it together with the mean to make, just to represent the data, really. All right, so the difference between what I did here, I have to regroup everything. So the difference between what we did here with this data set and what I'm going to do next, I use this term here. I refer to this data set as ex post or historical, because the data was collected and then I'm looking back and saying, well, this is data from the past, raw data from the past that I collected. So that's known as ex post, like after the fact, or historical, which is different from the second group of data. This data here is known as ex ante data. These data here are ex ante. What it says here is that there's only 5 possible outcomes, and they occur with this frequency. So this sort of data is different. It might use historical data. It might use some historical data on the state of the economy and predictions about the state of the economy. It could use information for the student, I guess, in terms of income for students, disposable income of students, and prospective income earnings. So this information would be all put together to derive what this is called a discrete distribution. There's only 5 possibilities, and they each have this likelihood. So this is called a discrete distribution. And it's different from me giving you data like this. Each of these observations here are equally likely. No one of them is more likely than the other. I'm just repeating myself. They each offer the same amount of information. They're different values, but they have equal significance. This distribution shows you the possible outcomes, and some of them are more likely than the others. 8 and 16 are more likely observations. Now, how do we analyze this kind of data? How do we summarize what is the mean and standard deviation of this sort of data? Notice above I have presented the formulas for you, and you see Greek letters again. Remember, what did I tell you? When you see Greek letters, it's because you're calculating parameters, okay? Assuming that this is the information about the population. So this is the population data represented as a discrete distribution. There's only 5 possibilities, and they have different likelihood. So this is based on a bunch of information that was compiled to come up with this distribution. So from here, I can calculate the mean, which is more general than the one that we just used. The one that we just used was the arithmetic mean, where we just added the numbers and divided by how many observations there were. Where in this case, these values are actually the only possibilities, and these are their probability of occurring. So what we can actually compute is the weighted mean. This is the weighted mean. What is the relationship between the weighted mean and the regular mean or arithmetic mean? Juan, are you asking about these? These are not percentiles. These are probabilities. P for probability. So these are the outcomes possible, and this is their probability. Okay, regular are more random. Okay, so that's something that you're talking more about the data. But again, they have the equal likelihood, right? I assume when I do this, I assume each of these are equally likely. In other words, what I've done, even though I didn't write it down, I could have put a PI over here, and each of these was or 0.2, right? Each of them would be 0.2. So notice I said to you that each of these are equally likely. So in essence, their likelihood is the same. So because it's a total of 5 possibilities, each are equally likely, Each of them have a probability of 1/5. So this formula here for the arithmetic mean could be written as the other formula, but the PI would always be 1 over n. So because it's always the same number, I don't have to put it over here. I can put it in the front algebraically. Do you follow me? So let me just take a moment for people who might not be following. Those are the values, right? And I divide by 5. But couldn't I have also done it's longer, that's why we don't do it this way. But I could have done that, right? So in other words, I could have also written this as or in general. So the formula that I give you for the weighted mean, oh, but I didn't use that symbol. Oh, I think I'm losing power. Did I lose power? My power went out on my other computer. Okay. Or in general, I write mu equals are you following what I'm saying? So this is pre-multiplying or post-multiplying each value by its weight. So I could write it like this, or I can write it like this, or in general, if the probabilities change, you have to write it like this. So that's why I write it like this. Any questions about that? And the reason why I use this symbol, again, was because this distribution represents the population, not just the sample. Of which there's only 5 possible. All right, so I feel like I have to write neater, but it takes too much time. Okay, so what we're going to do with this distribution is compute the weighted mean and the weighted standard deviation. This is best done in Excel. So maybe I'm going to cheat and go there, right? And then I'll put the results here. So 2, 8, 10, 16, 5. All right, let's put this in Excel. 0.2, 0.3. Is that right? Yeah. All right. So that's the data. These are the observations, which I denote as X. It always gives me a capital. And these are PI. Not sure why that happens. I'm going to just write prob. And what we're going to do is first let me make it a little bit bigger. Let's first compute the the mean. Okay, so the mean that's not going to be easy to write. So I have to write no, I have so much trouble. So X times PI. You multiply them, right? Going down. I'll do them better on the I'll do a better job when I transfer the results. So I multiply 2 times 0.2, so this is 0.4. This is 2.4. This is 1. This is 4.8. This is 0.5. Anyway, it's not pretty. I can't make it pretty here. Not sure how. All right. So what I've done is I've multiplied them together and then I'm going to sum them, and this will be the weighted mean. .1. So you see what I did? let's take this with me. I don't know if it's going to fit nicely. I can make it bigger. Let's put it here. Actually, I just need that. Oh, that's old. That's not right. No, it's not coming with me. So let's just finish it over here. So what happens? I want to calculate the standard deviation now. So it's a deviation from the mean all the way down. Then I square them. And then I have to do this multiplication again, because the formula for the weighted standard deviation is the average of the deviations from the mean. But the average is, again, a weighted average. So I have to multiply that here. I hope you've seen this before or something like it, because this is, you need to know how to do this, okay? So let's take the deviations from the mean. So this is I'm just going to put the number in there, 9.1, it's easier. And then I copy that all the way down. So that's the that's x, which is over here, minus the mean, which is over here. All right, so then what you have to do is take that and you have to square it. I hope you're following my notations. So I have to square that column. All the way down for the reason I explained before. So I have to square them, and then we need to average. But the average is a weighted average. So what we have to take is this column, and you have to multiply by the probability first, right? The probability. First or last, it's not that important when you're multiplying. So are you following me, Juan? I'm just following along. Do I? Yes, very good. Okay, so now we're going to pre-multiply. We're going to use this column. So always remember, I'm going to highlight this column because I'm not going to use that. going to fill that in with a color just so you don't look there. Well, or you do when you realize that's something else. So I'm always jumping over to, these values over here. So what I'm going to do now is multiply probability times this column. So I'm going to take the probability, multiply it by the squared deviation from the mean, and I'm going to do that all the way down. And finally, I don't have to divide anything, right? Because the probability is a fraction. It's already doing the job of getting an average for me. All I have to do is total. And when you total, you get the weighted variance. And once you have the weighted variance, you can get the weighted standard deviation. Because it's just the square root of this. Now our numbers look dramatically similar to what we had before, but we arrived at them with a different methodology, okay? A different method because the data was not like the other data. Each value, each observation had a different likelihood of appearing. So when I present data like this with different probabilities and I refer to it as ex ante, you have to make calculations like this. Now this one is in dollars. And also this one is in dollars. Oh, I guess it's 1.5. Okay. And then you would follow along with the same interpretation that we did before. On average, the student would have $9.10 in her pocket, give or take $5.15, and you can look for the likelihood of seeing certain outcomes appear. So when I tell you I've given you ex ante data and I give it to you with different probabilities of likelihood, I am giving you a distribution that you need to use to estimate weighted mean and weighted standard deviation. So all those numbers could go here. I guess I can put it here, but let's see. What happened last time when I did this? It did not appear, right? Oops. Oh, it worked this time. So I could just cover.
But you know, this is not great because then I don't have my calculation for the mean. I'll go get that too. And the calculation for the mean is using these columns here. I don't know, it's, yeah, yin yang. Anyway, positive, negative, give or take, yeah. Positive or negative, yeah. Give or take. Oh, I can't make this smaller. All right, so I hope you follow that. So most of the time she spends between, if you do the math, between 9, yeah, I rounded it up, $4 and $14. That's one standard deviation. So you need to know what to do with different types of data. I called this ex ante data to help you with a heading so you can recognize it, but you have to be able to recognize it on your own, okay? To know what to do. My data's off the chart here. Okay, there you go. Questions? Okay. No questions? So what's next? Do I have something under here? No. Very good. Okay, so I mentioned back here that you can use your calculator to practice statistical mode. You can, with statistical mode on your calculator, find the mean and standard deviation of this data set here. So you would have to extract the numbers, and anyway, you don't have to do it. You're gonna have enough practice in this class making calculation, but if you want to practice, it's a lot of numbers. Might be easier in Excel. So in Excel, you can also get the mean and standard deviations, all right? But I have to teach you how to use the calculator. That's my objective for this course. If you want to use Excel, that's fine too, but I expect you to be able to do both. All right. Maybe I can just stop here. I'm going to stop here, and then I'm going to start here next class, and then do this, and then the scatter plot stuff.
All right, because we spent an hour and 45. I think that's good. Any questions, Juan? So I'm going to post something in Connect right now for you to review the previous material, and I'm just going to ask you to read through these notes. And I'm just thinking maybe, I don't know, I'm just not sure, because if I do this now and students don't watch it, then I'm going to just go bolt into the new stuff. So I'm just gonna stop here, and maybe what I'll do is put some statistics questions into Connect. If I can do that, I'll look for those. Are you following along, Juan, so far? Do you want me to keep going? I just worry that students won't watch this video, and then I'm going to assume they know it, and then they don't, and it's very frustrating on both sides. All right. Yeah. Okay, so have a good weekend, and I'll be in touch. Read those notes so that you can have questions. It looks very menacing, but next week it'll come together, okay? And then we'll get into the new material as well. So have a good weekend and a good week. Bye for now.